Okay. So today we are going to talk about estimating distribution parameters. This will be a topic for the next exam, for the final exam. So everything up to extreme value distributions will be on exam 2. And then this and everything for the rest of the semester will be on the final. So our learning objectives for today, one, and that is to estimate parameters of probability distributions, PDFs or CDFs, from a sample of observations. So most of the problems we've been getting are, okay, say that some random variable follows a normal distribution with a mean and standard deviation, and then calculate probabilities based off of that. Well, now, and we've done this already to some extent, either in labs or some of the homework problems, where you're given a data set and you're asked to calculate parameters of the distribution. So if it's the exponential distribution, maybe we're calculating the average inter-arrival time. Or if it's the Poisson distribution, we're calculating the rate of arrivals. Obviously with normal distribution, it's pretty straightforward. We calculate the mean and standard deviation. Those are the two parameters of that distribution. And then we can fit that distribution to the data. So we're going to talk about what that actually is explicitly. And there's two methods we'll talk about. One is the method of moments. And moments, of course, refers to the first, second, and potentially third moments of a distribution. The first moment being the mean, the second moment, the variance, the third moment, the skewness. And so we can calculate mean, standard deviation, or variance, and skewness, and pretty much fit any distribution to a data set. And then from there, we can calculate probabilities of different values occurring. So one method is the method of moments. That's the most basic one. It's something that we've been doing already. The other method is called the method of, or the maximum likelihood method, or maximum likelihood estimators of these distribution parameters. That one's a little more complicated. We'll go through a basic example of that, but usually we're just going to be using our computational methods to calculate it, because outside of very simple examples, this method can get numerically complex. Okay, so say we have a distribution of sample observations. We can make a histogram of that to represent the distribution. And this would be our empirical. Can you guys see my mouse cursor when I do this? Okay, that's easier to do than the pen, so I don't move the paper. Okay, so we see that we can make a histogram, right? So density, probability density on the y-axis, the values of x on the x-axis. So really what we're trying to do is fit some sort of distribution or a curve to those data. And you've done this already in the labs, so we're just talking about what these methods are specifically. When we can fit a curve to the data, we're kind of estimating the population distribution with that curve and the population parameters with that curve. And we can do more kind of complex math, better estimation of probabilities when we fit a smooth curve to the data. So we're fitting a distribution function, like the normal distribution or log normal or exponential, to the sample distribution. And the sample distribution is represented by that histogram, which is just our data that we've collected. And with that fitted distribution, we can better calculate probabilities of certain events. Okay, so before we've had a lot of problems where it's saying, okay, wind speed, for example, has an exponential distribution with a mean speed lambda 5 miles per hour. So you're kind of given the distribution. You don't have data, you're just kind of given the parameters of that distribution. Or we could say the daily average discharge follows a log normal distribution with a mean of 100 CFS and a coefficient of variation of 10%. Then let's say find the probability that daily discharge will be greater than 1,000 CFS or something like that. So that's kind of like the approach we've been typically taking up to this point. now we're going to use our data, so a table of data, sample observations, and we'll estimate these parameters ourselves using the method of moments and the maximum likelihood method as well. Okay, so let's look at a bunch of distribution functions. And if we go to page 241, table 6.1 in our book, there's a huge table of distribution functions, some of which we've talked about in class, some of which we haven't. And each of these distributions has different parameters. So here's the PDF, here's the name, and then we have parameters. So the binomial and geometric really have one parameter, that's P, the probability of a success or failure, right? The Poisson distribution has this V term, which represents the rate. The exponential distribution has lambda, which is the one parameter for this distribution, which represents mean time, or average time. Then here's our normal distribution. We're familiar with these two parameters, mu and sigma, mean and standard deviation, and so forth. So what the method of moments does then is it says, okay, our mean and standard deviation, if we have a data set, we take the mean and standard deviation of that. We can relate the mean and standard deviation to these parameters that we're interested in. So if we have a bunch of observations of binomial outcomes, so say we're rolling dice and we're interested in the probability of getting doubles, we want to fit a binomial distribution to that. Well, we just roll all of our dice. We can take the mean number of times we roll doubles, say in a sample of 10. So n equals 10, and then we can calculate our probability based on that. Very, very straightforward. Things get a little more complicated when we get to these other distributions, and we'll go through some examples of this, like the log normal distribution, which the mean of our observations and the variance are related to the two parameters in this log normal distribution, not directly. So we've got to do some algebra to kind of figure out those. And that's what the method of moments is. It's really just figuring out the relationship between mean and standard deviation. In some cases, skewness gets thrown in there if you have a 3-parameter distribution. So most of the distributions that have parameters, like I said, that are related to the mean and standard deviation. Sometimes we need skewness if it's a more complicated distribution called a 3-parameter distribution. And we can estimate mean and standard deviation from our data. And then we can use the method of moments, basically just these equations that relate the distribution parameters to the mean and standard deviation. And we call it the method of moments again because mean, standard deviation are the first and second moments of a PDF. So for our mean, this is where we're getting into population estimates. So the expected value of the population, this kind of underlying theoretical distribution, is designated or denoted as mu, right? So mu of x is going to be the population mean, something that we're always trying to estimate with our data. We never can perfectly predict it. We're just assuming that there's some theoretical value out there, and every sample is going to give us an estimate of the mean and standard deviation of that. So we can estimate mu x, the population, from our data, and this gives us mu hat x. The hat just means it's an estimate. And we've done this before, very straightforward. Mu hat x is equal to x bar. This is our sample mean, and that is just 1 over n. So the sum of all of our observations divided by n. So we have 10 observations, we sum them up, divide them by 10. That's our mean, our x bar. And then with variance, sigma squared x is our population variance. We're going to estimate that with sigma hat squared x, or s squared. So s squared is our sample variance. And that is the sum of the differences between our observations and the mean squared divided by n minus 1. Okay, again, nothing we haven't seen before. The reason why it's n minus 1, this is called a bias correction factor. So let's just talk about what bias is. Bias of an estimator means that if we have an estimator, in this case, this is our estimator of the population mean, right? If on average that estimator is consistently over or under predicts the population value, and you can test this theoretically, then that parameter is biased, and so we have to correct that bias. So in the example of variance, variance is estimated originally by 1, so the sum of the differences between our observations and the mean squared divided by n. That on average is actually going to be underestimating the population variance. And so it can be proven theoretically that if you divide by n minus 1, this corrects for the bias. You'll see a lot more complex bias correction factors in different sample statistics, and we'll get into that next week. All right, so our first example here, we're interested in measuring velocity. And we know that velocity is a normal distribution in terms of if we got flow rate kind of going through a river, we put our velocity probe in there, and we're just sitting out there. The discharge rate's the same, but because of turbulence, the velocity is going to be fluctuating over time. So we take a bunch of velocity measurements here, and say we take 100 velocity measurements, 1 every second or something like that. And we know just kind of from past experience that velocity follows a normal distribution. And I forgot to write that back in with the mean velocity and the standard deviation of velocity. Okay, so we can estimate this mean and standard deviation by simply taking the mean of our velocity. So we say it's 2.9 feet per second. The standard deviation estimated by S is 0.6 feet per second. So if you look at the normal distribution, and let me just do something real quick here. Contrast is a little high for me. There we go. If we look at our normal distribution, it's going to be 1 over sigma square root of pi e to the -1/2. And this is v minus mean v over the standard deviation squared. So this is our normal distribution. And using the method of moments, we simply can plug in S for sigma and then x v bar for mu v. And same for down here. So very straightforward. We just plug those values in, and now we have a PDF that is fitted to the data. That's method of moments. It's very straightforward for the normal distribution because the mean and standard deviation directly plug into the normal distribution as parameters. So let's do a log normal distribution example, a little more complicated. So we have observations of the number of load cycles it takes to break an aluminum bar. So we've got this aluminum bar. The machine that it goes into is going to experience loading. So we do 75 trials, and we're just kind of pushing it, giving it simulating the load that it would receive under normal operations. All right, so we think that this loading cycle until failure, so the number of cycles it takes until it fails, follows a normal distribution for this particular kind of situation. All right, so X is going to equal the number of loading cycles until we get a failure. And we're saying that X follows some log normal distribution with a mean of Y and a standard deviation of Y. And Y is equal to the natural log of X. So we can use our method of moments then to estimate mu y and sigma y so that we can fit this distribution to the data. Okay, so we take our 75 samples, it's in a machine, it's getting those loads, and we calculate that the mean number of cycles until this bar fails is 26.75 million cycles. The standard deviation is 18.97 million cycles. All right, so pretty good. But now we want to know, the probability of failure given the cycles of loading that this piece might experience. All right, so X follows a log normal distribution right here. And then this is what the log normal distribution looks like. Very similar to the normal distribution. Now we have sigma y, we have X down here in the denominator. And then we have mu y and sigma y, and then ln of X. So using the method of moments, this is a little bit different than what your book shows, but it ends up being the same. Sigma y is going to be a function of sigma x and mu x. And then mu y is going to be a function of mu x and sigma y. So, just keep track of what the y's and the x's are. In this case, the x is the original data, and then the y is what we're calculating for the log normal distribution. So in this case, we would estimate sigma y first based on the standard deviation and mean of x. And then now that we know sigma y, we can calculate our mu y. So sigma y, we'll just plug our numbers in. And sigma y is going to be the standard deviation divided by the mean of the data. That's equal to 0.64. And then mu y is going to be the natural log of the mean minus the standard deviation of y divided by 2. So that equals 3.08. So now with our parameters, we can plug those in to the log normal distribution and supposedly fit that to our data. So that's method of moments. Do you guys have any thoughts or questions? The key is just figuring out what the relationship is between your mean and your standard deviation and the parameters of your distribution. And that's typically looking up in tables. When you go on the internet, PDFs are often shown in a lot of different forms. And so sometimes it can be a little complicated figuring out which parameter is what and how that's related. When you look up the log normal distribution, for example, you'll often see that equation with just mu and sigma in it, and then you got to read, okay, mu is actually the mean of the logs. Anyway, so it can get a little complicated in interpreting things. So it's just important to kind of keep track of the units, so to speak. Okay, so now we'll talk about maximum likelihood estimators. There we go. These are a little more complicated, and so I'll go through kind of a very simple example to illustrate how it works, and then we'll have a lab where we'll actually just use R functions to calculate these. Okay, so say we have a data set, and our data set is comprised of n observations, so x1, x2, all the way to xn. 10 observations, we'd have 10 x values. We want to find the set of distribution parameters, 1 or 2 or maybe 3 different parameters that define the distribution function that would most likely produce these data. So, sorry, what is the most likely set of distribution parameters that would produce this data? So we've got these observations, and then essentially what we're doing is weighting the probability of seeing those observations based on a given value of our parameter theta. So theta could be lambda if we're dealing with the exponential distribution. It could be the mean and standard deviation if we're dealing with a normal distribution. So if we put that another way, we could say what distribution parameter values result in a PDF that would produce that data set most likely. So to do this, we need a likelihood function based on our data. So xi would be our data set. And then the parameters, theta. So theta j is the different parameters we have. And we could have 1, 2, 3, potentially more parameters. Okay, so we need a likelihood function. And we'll just call that L. So L is our likelihood function. And L has all the data in it. So x1 all the way to xn. And it's got all of our parameters in it. So the parameters of the distribution, theta 1 all the way to theta m. So our likelihood function is really, all we're doing is we're taking a PDF evaluated at each observation. Okay, so f of x is our PDF. Say we think that the data fits a normal distribution. Okay, so we evaluate the PDF at x1 given this value of theta. Okay, so right now we're going to treat theta as a variable. X1 is some value that we have. And we're going to multiply that by the PDF evaluated at x2 multiplied by the PDF at x3 all the way to the PDF at xn. And the idea is if we multiply all these PDFs together, we're essentially getting a probability weighted function at each value or at each observation that we have. And so what that ends up being is a product function. So pi means product. It's the same as if we had sigma for S for sum. In this case, we're just multiplying each thing by itself or by the next PDF at that value. So again, these are values that we have from our sample, and this theta is just a variable that we're going to estimate. So now we need to find the values of theta such that this likelihood function is maximized. So the question is, what does it mean to maximize a function? Well, to maximize it, we take the derivative of it and we set that to 0. Where the slope of that function is 0, we know we have either a maximum or a minimum value. So the derivative of the likelihood function with respect to theta will equal 0 at the maximum value. So if this likelihood function, it's going to look like some sort of parabola. And it's going to have a maximum value, a peak. Our derivative will be 0 at that maximum value. And we'll evaluate that function for different values of theta. This is theta right here. So for different values of theta, we find a theta value that maximizes the function. Now, because the likelihood function is comprised of products, so all the different probability density functions multiplied by themselves, evaluated at a value of our data, it's easier to find the solution to solve for theta if we take the logs. So we end up with what's called a log likelihood function. And we're taking the derivative of it here. So the derivative of the log of the likelihood function with respect to theta. And so that's just how we'll annotate that. All right, so our log likelihood function, we have all our observation values. I is 1 to n. We have n samples or n observations in our sample. And then theta could be 1 value of theta, or it could be up to n values of theta. Usually we're just going to be dealing with like 1 or 2. So let's look at what this actually.
Hey, Joel.
Yeah.
What's in front of the log there? What is that?
So that's the partial derivative.
Oh, okay.
Yeah.
Thank you.
The partial derivative of the log likelihood function with respect to each value of theta or each parameter we have in theta. So we'll just go through an example where we have 1 theta. So it'll be straightforward. Okay, so we're sitting at a toll booth, and we're interested in the distribution of time it takes. How much time do we have between cars? How much time do we have to counter money and organize things and wipe down our stations so that we don't get the coronavirus. So we've got a sample of data, and the time between car arrivals at this toll booth, time t, ranges from 1.2 seconds all the way to 7.1 seconds. So we have 7 observations. Okay, so we know that inner arrival times typically follow an exponential distribution. It's just kind of from the theory. This is what our exponential distribution looks like. 1 over lambda e to the negative t over lambda. So the probability that our inner arrival time t takes on a certain value is a function of lambda. And so this is a 1 parameter PDF where lambda is the mean inner arrival time. So let's look at what our likelihood function is for this particular situation. So L of T1, T2, all the way to T7, and then our 1 parameter value is lambda. So because it's a product function, we're going to take the product from 1 to 7. So we'll have this PDF for each value of our observation. So 1 over lambda, there's only 1 parameter. EXP negative TI. So this takes on a value for each observation we have. So T1 is 1.2, T2 is 3.0, T3 is 6.3. So that equals, when we do all those products together, that equals lambda to the negative 7, right? Because it's 1 over lambda, and we're doing that 7 times, multiplying it by itself 7 times. And then when you do EXP times EXP times EXP, you end up summing everything, right? And the exponents. So it's lambda to the negative 7, EXP to the negative 1 over lambda times the sum of all of our times. That's in the exponent. So we just did the product 7 times, and this is what you get. Now, if we take the log of that, the log of L, we get, when you take the log of something with an exponent, the exponent comes down. So negative 7 log of lambda. And then when we take the log, or ln of E, that just gets rid of that E, right? And so now we just have what's inside of that. And in which case it's negative, the sum of all the times is 35.3 divided by lambda. So this is our log likelihood function. And this is the sum of all of our inner arrival times. So our next step is to take the derivative of the log likelihood function, set that to 0, and then solve for lambda. And this will be the value of lambda that maximizes the log likelihood function. All right, so the derivative of the log likelihood function with respect to lambda, and this is our log likelihood function right here, is going to be negative 7 over lambda. So the derivative of log of lambda is going to be 1 over lambda. Plus 35.3 over lambda squared. So that was lambda to the negative 1, multiplied by negative 1. Now we have negative 2 as an exponent. Set that to 0. And then we solve. So we can factor out a 1 over lambda. So that gives us 35.3 over lambda minus 7 equal to 0. And then we get 35.3 over lambda equal to 7. Lambda equals to 5.04 seconds. So what we did is we took a data set, we created this log likelihood function, and then we took the derivative of that, set it to 0, and solve for the value of lambda that maximizes that function. And so this value of lambda is, you can consider it a probability weighted value of lambda. That creates an exponential distribution that is most probabilistically speaking, would fit the data. Know that you could also take this data and calculate lambda as the mean of the data. So what's the mean of all these values? Just grab a calculator and do that real quick. All right, so 1.2 plus 3 plus 6.3 plus 10.1 plus 5.2 plus 2.5 plus 7.1 divided by 7. So the mean of that value is 6.6. So if we did this from a method of moments perspective, lambda would be equal to 6.6. So you get a different probability distribution, and you calculate different probabilities of different arrival times based on these two different methods. So this is our maximum likelihood estimator of lambda. And in general, the maximum likelihood estimator, or MLE, of lambda is just simply the sum of t over n. Maybe I didn't do that right.
For my mean, I got 5.05.
Yeah, you know what? I didn't do that right. Great. Okay. So turns out, guys, that the maximum likelihood estimator is actually the same as the method of moments. Sometimes they're the same. Okay. Thank you, Michael. Sometimes they're the same. So sometimes when you do method of moments, it's actually the maximum likelihood estimator. Not always, right? So this is a very simple example. When we get into more complex, like log normal and stuff like that, the maximum likelihood estimator will be different from the method of moments estimator. So things get more complex with different distributions. So we will use functions in R to calculate the maximum likelihood estimators for different distributions. The maximum likelihood estimator is typically better or more accurate than method of moments. Sometimes it's the same for simple situations. But a big part of this is we've been assuming the distribution. So you still have to assume what the distribution is of your data. We assumed that this was going to be an exponential distribution for our inter-arrival times. Sometimes we might not know what the best distribution is. That's often the case for extreme value distributions. You don't necessarily know which extreme value distribution is going to fit the best. So next time in class, next week, we'll talk about how we know our distribution is a good fit, and we can look at different distributions, how they fit to the data, and then determine which one we think is the best distribution. Once you determine which distribution you think is the best, then you can go back and do your MLEs, your parameter estimation, and go from there. So we assumed a distribution, and then we fit the parameters to that distribution using either the method of moments or the maximum likelihood estimator approach. That is what I got for today. Do you guys have any other questions, any thoughts? Okay, I'm gonna stop recording.